Welcome back, everybody. Today we're going to keep playing around with inverse functions. Last time we saw that a function has an inverse function, right? That reversing the arrows gives us a function if and only if our function is bijective. And so then if our function is bijective, then our inverse function f inverse is defined by the following rule, that f inverse of little b is a, if and only if f of a equals b. All right, so if we know that f of a equals b, then that tells us that f inverse of b is a, and vice versa. If we know that f inverse of b is a, then we know that f of a equals b. Well, today we're going to play around with a couple more situations, make a couple of observations, and work through the details in proving them. And the first observation comes from our basic picture here of our function f from a to b. Right, if f is bijective, well then f has an inverse function. Right, f inverse. But f inverse is a function. As part of our weekly work this week, we'll show that f inverse is bijective. And so it has an inverse function, right? That must map from a to b, right? F inverse inverse. Right, and our starting observation is that, hey, that's mapping the same direction as our original function f. Well, could these two functions be related? All right, and the answer to this is heck yes, they are related. And in fact, thinking about the flipping arrows idea, and if we reverse f's arrows direction and then reverse those, right, we're going back exactly the same as we were before. These should be dead on equal as functions. All right, but once again, this kind of intuitive idea with our arrows is fantastic and useful to have in our minds, but if we want to prove something, well, we have to do it legitimately, carefully, and completely, right, using our definitions and show what needs to be shown. All right, so let's start in. Here's our theorem 2. If f from a to b is bijective, then f inverse inverse equals f. All right, so to start in, we can suppose the hypothesis that f is bijective. All right, now let's think about, what kind of statement now are we trying to prove? What kind of statement is this? Well, it's got an equal sign in the middle, yeah? So it's an equality. What kinds of things are on the left and right-hand side? They're functions, right? So this is an equality of functions. And so there's actually a few things we have to check in order to say that these two are equal. Right, we got to check that they have the same domain and codomain, and that they give the exact same output for every input. All right, so domain codomain is pretty quick. We can note that f inverse maps from b to a, and so f inverse inverse is going to map from a to b. And maybe let me mention in here the comment we made just a moment ago. See if I can do a little text box. There we go. And f inverse is bijective by weekly work 9. All right, so it has an inverse function, and that inverse function is going to map Right, just reversing these from A to B. All right, so A to B, these two functions have the same codomain and domain. All right, next, we want to check that they have the same output for every input. Their inputs come from A, and so let's just take a general element in A and see where each of these functions sends it. All right, there's a little bit of yoga going on here, working with the inverse function definition. All right, so here's the idea. F inverse of A. All right, well, that's an inverse function evaluated at A. All right, that's going to give us some element of our codomain B. And well, what element is this going to give us? Well, thinking back to our definition of an inverse function, well, this function's inverse at A equals B. Well, that's going to happen if and only if this function sends B to A. Right? If and only if for us, where F inverse of B equals A. All right, it's a little bit weird because we've got these two levels of inverse functions, but right, we're just using our definition. Let me scroll back up. All right, F inverse of something equals something else. If and only if, right, the original function sends the output to the input. And over here, we got a function's inverse. We plug the A, well, it's going to output B if and only if the original function, which for us is this F inverse, reverses things, right, sends that output to the input. All right, well, let's continue unwinding. All right, F inverse of B equals A, well, that tells us something about F, right, that F must send A to B. So F inverse of B equals A implies that F of A equals B. And we do a little comparison here. F of A equals B, and F inverse of A equals B. Well, and therefore, F inverse of A equals F of A. All right, and that was our last check we need to make, that they give the same output for every input. We verified that, and hence, these two are equal as functions. All right, let's consider a second situation where we actually have two functions lined up in a row. All right, so here, say that we have a bijective function from A to B, and that G is a bijective function from B to C. Well, if that's true, right, well, one thing we can do is we can look at their composition. It's going to map from A to C. Right, that'd be G composed F. That's the thing on the right goes first. And right, from our group work in section 6.4, we know that if F and G are bijective, then the composition is going to be bijective as well. All right. Well, since F is bijective, we'll have an inverse function. Since G is bijective, we'll have an inverse function. And now we have two pink functions in a row. If we wanted to, we could compose them. All right, so the one that goes first is the G inverse. So G inverse F inverse. So F inverse composed G inverse. But also, since G composed F is a bijective function from A to C, it has an inverse. All right, it's going to have some inverse function from C to A. All right, this is going to be G composed F inverse function. All right, and now this green function is going the same direction, the same domain codomain as this pink composition. And so our question is, hey, are these related? All right, is G composed F inverse related to F inverse composed G inverse? And once again, the answer turns out to be absolutely. In a very strong way, these also are going to be equal as functions. All right, and this gives us a statement of theorem 3. If F and G are bijective, then G composed F inverse equals F inverse composed with G inverse. All right, a couple of notes before we dive in and prove this. The first is comparing the left-hand side with the right-hand side of this equation. If we look at G and F, well, on the left, G is on the left, F's on the right. But if we look on the other side, things have flipped. Right? The order of F and G reverses as we move from one side to the other in our equation. Kind of algebraically, what this means is if we are inverting a composition of two bijective functions, if we want to kind of distribute this inverse, well, then we have to reverse the order of the functions inside. Kind of a computational way of thinking about it. And I claim that this makes a lot of sense if we think about an inverse function as a function that somehow undoes the original function. Right? And thinking about it this way, this property, this theorem, is sometimes called the socks and shoes property. Right, the idea being, well, if you, in the morning, you put on your socks and then put on your shoes, and then you want to undo that, well, you got to deal with things in the reverse order, right? You first got to take off your shoes and then take off your socks. All right, so the idea is F is, putting on your socks, G is putting on your shoes. Well, if you want to undo that, well, then you have to first take off your shoes and then take off your socks. That's a real name, by the way. I didn't make that up. All right. With those notes noted, let's go ahead and prove this. Once again, we can start by assuming the hypothesis that F from A to B and G from B to C are bijective. All right, and then from there, what kind of statement are we trying to prove? Well, once again, we have an equality of functions. So we got to check same domain, codomain, and that these two functions give us the same output for each and every input that we hand them. All right, so just a little bit of bookkeeping to check same domain, codomain. To start, though, let's make the observation that we made before, that if F and G are both bijective, well, then their composition, right, G composed F, is going to be bijective, right, by our 6.4 group work. Right, and if that's true, then the composition has an inverse function, and it's going to be mapping the other direction. Right, G composed F inverse is going to map from C to A. right, next let's build up to our F inverse composed G inverse. Right, G inverse is going to map from C to B. F inverse is going to map from B to A. So if we compose these two, we're going to map from C to A. All right, and so it's the C to A that we are happy to see. So our two functions do indeed have the same domain and codomain. All right, next, to see that they give us the same output for every input, let's hand each function a kind of a general input from our domain, big C. All right, so let's let C be in C. It's going to be helpful at this point to kind of move this around a little bit. If I slide up to our diagram, right, our little c is hanging out here in our right-hand set. Well, if we want, we can send it through our G inverse to get an element here, and then send that through our F inverse to get an element over here. Let's take a minute and introduce these. All right, so then G inverse of C equals B, right, where G of B equals C. Right, this is just using the defining property of inverse functions. And similarly, we can take this B and send that through F inverse. Right, F inverse of B is going to be some A, where F of A equals B. All right, so with this kind of groundwork, let's take our element C and let's maybe first send it through our composition here, F inverse composed G inverse. All right, F inverse composed G inverse of C, by definition of composition, is F inverse of G inverse of C. Right, but G inverse of C equals B. And so we can substitute that in to get F inverse of B. But hey, F inverse of B equals A. And so let's substitute that and see that we get A. All right, so that's the result. That's the output of plugging our input into our function. Let's check our second function, the G composed F inverse. All right, if we plug, oh yeah, I just confused myself. Right, if we want to see where G composed F inverse sends, let me do it like this. G composed F G composed F inverse of C, equals something, right, where G composed F of that something equals our C. And so here we can kind of see, maybe if we go up to our diagram, once again, right, so we had our C here on the right, we sent it through G inverse, got our B, send that to A. Well, what is G composed F going to send to C? Well, it's got to be our A, right? Because if we send our A through F, we're going to get B, and then it'll send it to C. So that's what we're looking for. All right, so since G composed F of A, by definition, is G of F of A, all right, but F of A, looking up to our kind of bookkeeping notes here, F of A equals B. So this is G of B. And G of B equals C. So we know where G composed F sends A. It sends A to C. Therefore, G composed F inverse is going to have to send C to A. All right, therefore, we have G composed F inverse of C equals A. And check this out. All right. We can see now that both our functions are indeed giving the same output of A, right, for the input of C that we've plugged in. So at this point, we can say that, hey, these two functions gave us the same output for our general input C. And that was the last thing to check. We can now say that these two are indeed equal as functions. All right. That's it for today. Good work, everybody. I'll see you next time.